Hi guys, today we're going to be taking a look at orbitals and energy levels. So the first thing that we're going to be doing is that we're going to be looking at the O-level electronic configuration. So we're going to start off with sodium. The proton number for sodium is 11, which means that the total number of protons in the nucleus is going to be 11. And the total number of neutrons in the nucleus are going to be 12. Since the proton number is 11, the number of electrons that you're going to have in the shell are also going to be 11. So I've drawn those electrons, and these white circles represent the electrons. So in the first shell, you have 2 electrons. In the next shell, you have 8 electrons. And in the valence shell, you have 1 electron. Now this is the O-level electronic configuration, and we studied that there's going to be fixed shells or fixed orbits, and these are going to contain electrons. Now in A-levels, this is not exactly the case. So this is the A-level electronic configuration. As you can see, there's no fixed region for these electrons. There's just going to be one region, one area. Like over here, you have these fixed circles, fixed orbitals drawn. So these, in A-levels, it's not fixed. So it's going to be one region. Instead of being one circle or one line, it's just going to be one region. And the region is represented by the green dots that I've made over here. And this region is going to be where an electron spends 90% of its time. And this indicates the probability of finding an electron at any given point. So when an electron has suitable energies, it is set to occupy that orbital. So you can even have another orbital outside this, in this region over here. And if your electron possesses more energy, it can be in this region. So the main purpose of this slide is to show you that the O-level electronic configuration is this, and the A-level electronic configuration is a little bit different. So in this region over here, you can still have some electrons. It doesn't mean that there's going to be no electrons in this region. It's just that the probability of finding an electron over here is going to be lesser. So now we're going to be talking about orbitals in a little bit more detail. So you have two main types of orbitals. There's going to be an s orbital and a p orbital. And now we're going to be discussing their structure and a little bit of their properties. So an s orbital is going to be spherically shaped like this. So you have 1s, 2s, which is going to be a little bit bigger than 1s. As you can see, this circle is bigger than this circle. And then you have 3s, and then so on. So 3s is going to be bigger than 2s. You can have 4s and 5s. I've just drawn 3 of these. Then we have a p orbital. Now a p orbital is different in the sense that an electron density is concentrated in particular regions along a straight line that passes through the nucleus. So this is your straight line, and electron density is concentrated in these particular regions. So you have px, in which the straight line that's cutting through the nucleus is the x-axis. You have py, in which the straight line cutting through the nucleus is the y-axis. Then you have pz, in which the straight line cutting through the nucleus is the z-axis. So this was s orbitals and p orbitals and their descriptions. Now we're going to be taking a look at energy levels. Now energy levels is also another name for the main shell or the principal quantum number. So the main energy levels are going to be numbered 1, 2, 3, 4, 5, 6, and so on. And they're going to increase as you move away from the nucleus. So if you are close to the nucleus, the energy level that's the closest to the nucleus is going to be 1. If you move away, it's going to be 2, 3, 4, 5, and then so on, like you saw in the previous point. Now each energy level is going to consist of sublevels. So if you have energy level 1, it's going to have its own sublevels. If you have energy level 2, it's also going to have its own sublevels. And the number of sublevels is equal to your principal quantum number. So if your quantum number is 1, you're going to have 1 sublevel or subshell. If your quantum number is 2, you're going to have 2 sublevels. So this depends on the quantum number. And these are the names of the subshells. So at 1, you're going to have 1s. At 2, you're going to have 2s and 2p. At 3, you're going to have 3s, 3p, and 3d. And the details of d orbitals are going to be covered in A2. At 4, you're going to have 4 subshells, which is s, p, d, and f. And the details of f are also going to be covered in A2. So now we're going to be taking a look at a detailed example of what we previously discussed. So this is quantum number 2. Since it's the second quantum number, it's going to have 2 subshells, right? Which we saw previously. So it's going to have 2s and 2p. Now at each quantum number, you're going to have orbitals, which contain electrons. So this is your 2s orbital, and over here you have p orbitals. So you're going to have px, py, and pz, like I discussed before. And inside these orbitals, you're going to have electrons. And in the next video, we're going to discuss how to arrange electrons. So just to recap, you have a principal quantum number. At that quantum number, you have subshells. And the number of subshells is going to be equal to whatever the quantum number is. Each quantum number is going to contain certain orbitals. So whenever you have the p subshell, it's going to have 3 orbitals, which is going to be x, y, and z. And for s, it's just going to be 1 orbital because it doesn't have any directional properties. So these are going to hold a certain number of electrons. Now, if you want to find the number of electrons, it's just going to be the quantum number squared. So over here, it's going to be quantum number 1 is going to contain 1 electron, 1 orbital, sorry, not electrons. Quantum number 2 is going to have 4. So if you want to find out the total number of electrons or orbitals, you're just going to square the quantum number. One more important thing to note is that as your quantum number or as n becomes larger, the spacing between successive shells becomes less. So if there was a certain distance between two shells earlier on, as your quantum numbers increase, that difference is going to decrease. And this leads to overlap of energy levels. As you can see over here, you have 1s, 2s, 2p, 3s, 3p, 4s. Now after 4s, you directly have 3d and 4p follows after. Now this is because of the overlap of energy levels.